Okay, you guys are still seeing my screen?
Yes, sir.
All right, so let's move on. Okay, so the reactions of aromatic compounds. Now, what we are going to learn, say, right? What we need to know are the reactions of benzene, which are halogenation and nitration reactions. What we need to know other than that is the reactions of toluene, which is methylbenzene, halogenation and nitration. We need to know the nitration, bromination, and reduction of nitrobenzene using tin and hydrochloric acid for the reduction, right? We must know the reactions of phenols with sodium hydroxide, acyl chlorides, and aqueous bromine. And we must know the reactions of the primary amines, right, like that with nitrous acid. We're going to look at them, and we're going to have a look at the azo compounds. That is what we're going to learn today. All right. So, what are you supposed to know? All right. I spoke to you guys before about this, or messaged you guys in the group about this. You must know Lewis structures, formal charge, molecular geometry, resonance, and polar and nonpolar bonding. If you don't, this topic may not be understood by you. No matter how you try, it's not going to work. Right? So, did you guys actually read up on these topics? Do you guys know these topics? All of them from Module 1 Chemistry.
So I watched some videos today.
All right, no problem. Okay. Anybody else have any issues with what is happening here? Any issues here? What is the major issue here? Is it resonance? Let me check
Sir,
something.
I understand all of them except formal charge. I need a little bit more clarity on that, but I understand the other four.
All right, lovely. Because formal charge is actually probably the least one that you don't really. But we're going to talk about it. A little. We're not gonna go into the calculating it, right? But it is important that you understand it, right? But you should be able to get through this. You should be fine. But the key things that you can't get through this with are these. You're not going to work if you don't know those, right? But if you have a question, you know you can always ask, right? Whether or not you understand it, if you have a question, just ask. All right. Somebody raise their hand. Go ahead.
Sir, I did everything except molecular geometry. Is that where like you tell the bond and the angles? Jeez, that's
Yeah,
them by.
bond angles and stuff like that.
Oh,
For
okay.
example, if we have a substance like ammonia, we're going to end up with a structure like this. Or is electron geometry, we're gonna have 107 degrees and so so something like this. And this is trigonal, pyramidal, right? Those type of things. All right. But it's basically we're going to be looking at the planar structure and what Keklu was talking about, right? Let's talk about it. Aromaticity, right? Eric Hugo was the main person that was talking about this, right? So the underlying criteria for aromaticity. What is aromaticity? Aromaticity speaks to the fact that these compounds display resonance, right? That they have resonance structures. They are ring structures, right? That contain benzene-like derivatives, right? So they have what we call a Kekule structure, right? So it has that type of structure where it has some double bonds and it forms a ring system of 3D localized p or pi electrons, right? We're gonna be using these terms. That's why I recommend that you guys looked at resonance before. All right. So the underlying criteria for aromaticity, remember that we're not talking about aromatic compounds as in sweet smelling compounds, right? Sweet smelling compounds are esters. They are not aromatic compounds, right? So aromaticity does not speak to the smell of the molecule. No, it does not. It speaks to the fact that it can display some amount of conjugates, effect, and resonance structures. Right? So as I'm saying now, the underlying criteria for aromaticity was recognized in the early 1930s by Eric Huckel. All right? Based on the molecular orbital calculations, we're not going into MO theory, because MO theory is some different type of chemistry, right? It's lovely chemistry, but it's some different type of chemistry, all right? So to be aromatic, we must meet these four criteria. If we don't meet these four, we're not aromatic. So first of all, we must be cyclic. We must be cyclic. If we're not cyclic, we're not aromatic. Therefore, esters are not aromatic. So you must be cyclic, all right? Second, we must have one p orbital on each of the atoms in our ring, meaning our carbons must be sp2 hybridized. Must be sp2 hybridized, right? Three, it must be planar in nature or nearly planar so that there is continuous or nearly continuous overlap of all p orbitals on the ring for our p system of electrons to allow resonance structures to emerge. And four, we must have a closed loop of 4n plus 2 pi electrons in the cyclic arrangement of p orbitals. All right. So this is how we know if a substance is aromatic. Firstly, if it is not a ring, throw it away. It is not aromatic. Don't fool yourself. All right. If the carbons don't form a ring that has sp2 hybridized capabilities, it is not aromatic. Throw it away. Right? So if you're looking at a ring structure like cyclohexane, that is not flat. That is not flat at all. And their carbons are actually sp3 hybridized, therefore they're not aromatic. It must be sp2 hybridized. Right? And it must be flat or near flat, or what we say planar or near planar. Alright? The aromatic compound is important, and these are what we call arenes. And the reactions of these compounds are what we're going to be describing. Okay? Following so far, guys?
Yes, sir.
Yes, sir.
Right. Okay. So we're going to be looking. This is what we have here. As um, what is it called again? I always pronounce the name wrong. Kekule's principle, right? So it is actually benzene is actually the thought of a dreaming chemist, a daydreaming chemist. The man was just there one day trying to understand how H6 or C6H6 behave this way, and he daydreamt of a serpent eating itself. Right? So he's thinking now that this C6H6 forms such a structure, such a cyclic structure, in which it continues to move, the electrons continue to move round and round, right? Within that cyclic movement, within that type of circular motion, right? Within any direction it may please. So this is what came to mind in his daydream, and this is how we understood the structure of benzene. This is how the structure of benzene came to light, right? Through a daydream, right? But now we have to study it. Right, so this is the actual structure of benzene. This is how benzene looks, right? So this is how we have our C6H6 being presented, right? We have our carbons. They're all sp2 hybridized, right? That means they have planar structures, right, all around the ring. And we notice that since they're sp2 hybridized, we have free p orbitals on each of the carbons, right? And these free p orbitals allows for the overlap around the entire system. So we have orbital overlap. This is from unit 1, guys, just follow through. We have p orbital overlap that allows for electrons to travel and exist on all 6 carbons and not to be centralized on one carbon. And that is important for resonance and conjugate theory. All right? So it's just we know that the electrons are existing across the entire ring structure. All right. So we're gonna be looking at this. This is just one conjugation of benzene, by the way. You could have benzene in which the double bonds are located like this, right? So if we erase one of the bonds from here, the bonds could shift. And that is why benzene is usually denoted by just a ring in the middle, showing that the double bonds continue to switch places as electrons move around the ring. Notice I'm using full-head arrows. Electrons continue moving around the ring, so the double bonds will be found on different places. So all we do, we just simplify that in what we call the hyperconjugated structure of benzene. And we're going to get into all of that because it's on the slides following. All right? Am I moving too fast? Am I moving too slow?
Sir, too slow, but alright, you can continue.
Too slow. All right. So let's move on then, right? Everybody's fine so far? Are we ready to get into benzene? Just drop a one in the chat if you're ready to move on. All right, let's go for it. Benzene. The structure of benzene has a six carbon ring with three double bonds, right? I would say three doubly bonded carbons, but whatever. Three double bonds proposed by Kekule, right? So he suggests that there are two forms of benzene in equilibrium which different positions of double bonds. That is what I was alluding to, right? However, this did not explain the fact that all carbon-carbon bonds in benzene are the same length. We know from Unit 1 that double bond carbons and single bond carbons have two different bond lengths, right? So how can all the bonds in benzene be the same length? Since the double bonds are separated by single bonds, it means that structure involves conjugation, right? So let's have a more in-depth look at what this is, all right? So it's on the slide, but let me copy it and move it to a new slide and let's magnify it, all right? Let's get the magnification, real image over the object over the image, all right? Let's get this. Okay, love that. And let's have a look at this. The hyperconjugation of benzene we're going to be looking at. So looking at this now, Kekule's structure, right? His structure. So we're saying that is either the double bonds can exist here or the double bonds can exist here. So notice that they switch positions, right? So what he's basically saying, is that these are two isomers of benzene. The double bonds are on different areas. They are functional. They're not functional group isomers. They are positional isomers, right? So what he's saying now is that we could just gain a hyperconjugation. We could just say that this is a simplified depiction of benzene. So instead of we describing benzene as one of the two isomers, we just use a simplified depiction of the hyperconjugated benzene, right? So these are different structures. These are different ways in which we see benzene. These are literally one, two, three, four, five, six, seven ways of depicting benzene, right? And we will usually depict it this way, right? This is the usual depiction that we will use in this entire session, all right? Any issues, any concerns?
No, sir.
Right. As the guy said, I'm moving a bit too slow. I apologize for moving too slow. All right. So let's look at this. Benzene is the simplest aromatic hydrocarbon. All right. Benzene has 4 degrees of unsaturation and those type of things, making it a highly unsaturated hydrocarbon. Whereas unsaturated hydrocarbons such as alkenes, alkynes, and dienes readily undergo addition reactions. Benzene does not. All right. So benzene requires a little more, energy, right? So these are some derivatives of benzene. So we have something like toluenes, phenols, anilines, acetophenones, benzaldehydes, benzoic acids. benzonitriles, orthozeniles, and styrenes. You guys would have known styrene from what we call polystyrene or foam boxes, right? You guys would have known toluene used as a great organic solvent, right? And this is what methylbenzene is. You guys would have known phenol as well, right? All right. What else would you guys have known before? You guys wouldn't have really looked at anything else really, but these are different um derivatives of benzene that we would have looked at before. All right. So the structure of benzene, we looked at it already. We're just gonna be moving past this. All right. So looking at this again. So how does the reaction of benzene really occur in this way? Right? So the addition reactions that benzene occurred. Benzene is unsaturated, therefore it undergoes addition reactions, right? Electrophilic additions, right? We might add. So electrophiles tend to attack the benzene ring system, right? But in all cases of aromaticity, the ring is preserved, right? So this means that the electrophile enters and a hydrogen leaves, right? So it's not that. So if we have an electrophile adding, we what happens here? What happens to the carbon here? So if we have a carbon here, right? Let me just draw a little bond. If we have a carbon here and we have a hydrogen here, right? What hybridization is the carbon in? What hybridization is the carbon in?
Yeah.
Repeat.
I'll say sp3 because um the hydrogen, well, we are considered double bond as well, sir.
Wait, I'm just asking what is happening here. So let's say this is connected to a R group, this is connected to a R group. Let's just consider the R group the rest of the ring. Alright? What is this carbon's um hybridization?
Well, sp3.
sp3. Interesting. Any other takers? Any other takers? Everybody agree with sp3? Everybody lost? Alright. I find it hard to believe that Unit 2 students are lost in chemistry. Nobody has an answer. Alright, so the carbon is sp2 hybridized. Right? So it's sp2 actually. sp2 hybridized is connected to three bonds. That's three bonds. If it's sp hybridized, it would have been connected to two bonds. If it is sp3 hybridized, it would have been connected to four bonds. So it's sp2 here. And we note that sp2 carbons are what we need for aromaticity to occur. Alright? Going back to the principles. Huckel's principles, right? It must be sp2 hybridized. Looking at that, right? So what we're saying here now, what this slide is saying is that when we have the electrophilic addition of anything, when the electrophile adds to the carbon, what it does is break the aromaticity of the ring. It creates a positive charge. And that positive charge will continue being shifted around the ring, right? Until the hydrogen leaves. Because when the electrophile adds, it becomes sp3 hybridized, breaking the aromaticity of the ring. The ring is now unstable. In order for the ring to remain stable, we must lose something for the carbon to return to sp2 hybridization, and the hydrogen will leave for it to return to sp2. So now it's sp3. When the hydrogen leaves, it returns back to sp2 and stability is restored. So if you look at the diagram up here, the electrophile is added, right? So what happens now? We break a double bond. That's what's happening now. We break a double bond. So we see the positive charge being centered there. So the positive charge will actually continue to be moved around the ring. So we see it's moving around the ring, and it will continue to move around the ring as the ring is destabilized. Because we know that we don't want a charge on any specific carbon. What we're having is a positive charge moving around the ring. We don't want that, right? And it will continue to move within these different resonance stabilized ions until the hydrogen has been removed from the ring, restoring stability. Can we appreciate that? Can we appreciate that? I think we'll be able to appreciate it a little bit more when we look at the bromination of benzene. But can we appreciate it thus far?
No.
No? Alright. So what we're going to do now, we're going to hold on to that a second, right? We're going to look at a reaction, the halogenation of benzene, and then I'm going to go back to it and ask you guys if you understand. Fair?
Okay.
Yes, I didn't hear the question.
Okay, what I was asking if you guys understood what is happening here and why hybridization breaks the
Yes,
ring.
sir, yeah.
Oh, you understand it. Okay. Some persons
Yes.
don't, but what we're going to do the halogenation of benzene, and then I'm gonna ask a question about it. All right. Okay. So let's have a look at the halogenation of benzene first. Hopefully the thing is recording. I noticed that there have been issues with the recordings and stuff like that. So if the recording has been corrupted and whatever, then I apologize. We'll just have to remember. All right. So let's get this on board. So the bromination of benzene, we know already. Let me just go back here. Where was the information? Look at this information here. Look at it. Not don't even look at it. You must see the information. Look at it. Whereas unsaturated hydrocarbons such as alkenes, alkynes, and dienes readily undergo addition reaction, benzene does not. Why is that? It is because of the stability of benzene. Benzene is one of the most stable organic compounds you will. No, never mind. Benzene is the most stable organic compound you will discover in Unit 2. Benzene cannot react so easily with electrophiles. It has standards, right? You need to have an extremely strong electrophile in order to add itself or add the electrophile to benzene. Benzene doesn't take any and any electrophile like that, right? So looking at this now, benzene requires an Lewis acid in order to actually have a bromination or a halogenation. It must have what we call a Friedel-Crafts catalyst. All right? Let me write it. A Friedel-Crafts